Hello, I am Dr. Gajendra Bedare, Department of Physics, NS Science and Art College, Bhadravati, District Chandrapur, Maharashtra. My topic is elasticity. Let us see which topics I am going to discuss here. The first one, that is the introduction. Second one, stress, then strain, then Hooke's law, and the last one, that is modulus of elasticity. There are different mechanical properties of material. Elasticity is one of them. In introduction, we discuss few definitions which are important in understanding elasticity. The first definition, it is of deformation. Let us take simple example of rubber band to understand the concept of elasticity. When we stretch the rubber, there is increase in length of the wire. We stretch the rubber band, that means we are applying the external force, but when we release the rubber band, it comes to original shape and size. Let us see the first definition. When external force is applied on material bodies, produce a change in shape and size of body. Such a change is called deformation. Deformation consists of change in dimensions of the body. Second definition, it is a deforming force. As we have seen the example of a rubber band, we applied the external force, we stretch the rubber, and because of that there is increase in length of the rubber band. So the definition of deforming force is that the forces which produce deformation are called deforming forces. This deformation may be change in length, may be change in volume, or may be change in shape. The next definition, that is the elasticity. It is the property of material body by virtue of which it opposes the change in shape and size and regains its original shape and size after removing the deforming force is called elasticity. As we have seen the example of a rubber band, when we stretch the rubber, that means when we apply the deforming force, there is an increase in length of the rubber band, but when we release the rubber band, it comes to its original shape and size. It is elasticity. The next definition, that is the restoring force. As we have seen in the example, when we remove the external force or when we release the rubber band, it comes to its original shape and size, and that is because of the internal forces in the rubber band. So the definition of restoring force is the internal force in a material body which opposes the deforming force and due to which the body regains its original shape and size is called restoring force. Then what is perfectly elastic bodies? The bodies which can recover their original condition completely on removal of deforming forces are called perfectly elastic bodies. Next definition is elastic bodies, or again plastic bodies. Bodies which do not show any tendency to recover their original condition on removal of applied forces are called plastic bodies. The next one, it is stress. When deforming forces applied to a body, the body undergoes change in shape or size. In this constrained state, the body tries to restore its original position. These internal forces developed are equal in magnitude to deforming forces and acts in opposite direction to the deforming forces. That means we stretch the rubber, that means we are applying the deforming force, and when we release the rubber, the internal forces are set up within the rubber band, which brings that rubber band to the original shape and size. Here the deforming force and restoring force, they are equal in magnitude, but they act in opposite direction. Stress, again we can define. The stress is defined as the force applied or restoring force per unit area set up inside the body within elastic limits of the body. Thus we can write the formula: stress equal to force upon area. So SI unit of stress is for force Newton, for area meter square, that means Newton per meter square, and CGS system, its unit is 9 per centimeter square, and this is the dimension. There are three types of stress. The first one, that is longitudinal stress, second one volume stress, and third one is shear stress. First we will see what is the meaning of longitudinal stress. Whenever there is a change in length of a body, the longitudinal stress comes. If the definition, if the deformation consists of change in length, then the stress is called longitudinal or tensile stress. The formula for longitudinal stress is F by A. For this we take the example of a wire fixed at one end or at the upper end, and the load is attached at the lower end. Because of the load attached, it acts as a downward force, and there is an increase in length of the wire because of that downward force. So we can this weight attached, it acts as a downward force, and weight, it is denoted by mg. So we can write the formula for longitudinal stress, F by A equal to mg upon pi r square. Here mg is the weight attached to the wire at the lower end, and pi r square, it is the cross sectional area. The second type of stress, it is a volume stress. If the deformation consists of change in volume, then the stress is called volume stress. Volume stress, again, it is equal to change in pressure, and it is denoted by dP. So for this we take the example of a balloon. When we insert the air, that means we are changing the pressure, and because of that there is a change in volume of the balloon. The third is the tangential or shear stress. The tangential force develops a change in shape. Stress produced in it is called tangential or shearing stress. Thus, when deforming force acts tangentially over an area of the body, gets sheared through a certain angle. Then the next one is strain. How will you define the strains? When a body is under a system of forces or couple of forces in equilibrium, then change is produced in dimensions of the body. The fractional change or deformation produced in the body is called strain. As we have seen, this deformation may be change in length, change in volume, or change in shape. So strain is defined as the ratio of change in dimension to the original dimension of the body. Strain, it is a dimensionless quantity. Strain, it is also of three types, as we have seen stress having three types. The first one, it is the longitudinal strain, second volume strain, and third is shear strain. First, the longitudinal strain. It is defined as the ratio of change in length to the original length. As we have seen the example of a wire fixed at upper end and the load is attached at the lower end, then capital A is the original length and small l is the change in length. Then longitudinal strain, it is equal to change in length upon original length, that means small l upon capital L. Second one, it is a volume strain. It is defined as the ratio of change in volume to the original volume. We have seen the example of a balloon. Then volume strain is defined, it is equal to change in volume upon original volume, that means dV upon V. The third is shear strain. If the deforming forces produce change in shape of the body, then the strain is called shear strain. We will discuss shearing strain in details. If the deforming forces produce change in shape of the body, then strain is called shear strain. For this we take the example of a box which is fixed at the lower surface, and on the upper surface if the tangential force is applied, the upper surface BC, it gets shifted to the new position BC dash. The shearing strain, can also be defined as the ratio of lateral displacement x of the corner B to the transverse dimension L. Thus we can write shear strain, it is equal to x by L, and it is equal to tan theta. Theta is the angle through which the upper surface get shifted. In practice, since x is much smaller than small l, so tan theta approximately equal to theta, and the strain is simply the angle theta, which is measured in radians. So we can write shear strain equal to theta. The next one, it is the Hooke's law. Hooke's law, actually it is a relation between the stress and the strain. Hooke's law, it is the fundamental law of elasticity and stated as within elastic limit, stress is directly proportional to strain. So we can write stress proportional to strain, or stress upon strain equal to constant, and it is equal to capital E. Capital E is known as modulus of elasticity or elastic constant of a given material. So modulus of elasticity, we can write the formula as modulus of elasticity equal to stress upon strain. If we plot the graph between stress and the applied stress within the elastic limit, we get the straight line as shown in the figure. In figure, on the x-axis there is applied stress and on y-axis there is strain. The modulus of elasticity depends on the nature of materials. Units of modulus of elasticity are same as those of stress, as we have seen, that is Newton per meter square, and dimension is given here. Again, there are three types of modulus of elasticity similar to stress and strain. There are three different types of stress and strain related to the change in length, change in volume, and change in shape. So there are three different types of modulus of elasticity. The first one, it is Young's modulus. Second one, bulk modulus, and third is modulus of rigidity. So first we'll see Young's modulus, which is denoted by capital Y. Young's modulus of elasticity, it is the ratio of longitudinal stress to the longitudinal strain. Second is bulk modulus, which is the ratio of volume stress to the volume strain within elastic limit. And third is modulus of rigidity, it is denoted by eta. The modulus of rigidity, it is the ratio of tangential stress to the shearing strain within elastic limits, and it is called modulus of rigidity. First, Young's modulus, we will discuss it in details. Young's modulus of elasticity, it is the ratio of longitudinal stress to the longitudinal strain, as we have seen already. For this, to explain the Young's modulus, again we are taking the same example of a wire fixed at upper end, and to the lower end the weight is attached. Weight attached, it is mg, and because of that there is an increase in the length of the wire. Capital L is the original length of the wire, and after attaching the load there is small increase in length of the wire, and that is small l. This weight attached, it acts as a downward force. So we can write longitudinal stress equal to F by A. F by A equal to mg upon pi r square. Here mg is the weight attached to the lower end of the wire, and pi r square, it is the cross sectional area. Again we know longitudinal strain equal to small l by capital L. So from the above equation we can write Young's modulus equal to longitudinal stress upon longitudinal strain. Longitudinal stress means F by A, and longitudinal strain small l by capital L. So we can write the formula Y equal to mg upon pi r square, which is the longitudinal stress, and small l by capital L, it is the longitudinal strain. So we get the last formula Y equal to mg capital L upon capital A small l. Unit of modulus of rigidity is Newton per meter square. The next is bulk modulus, which is denoted by capital K. When uniform force is applied to normally on the surface of complete body, it produces change in volume without any change in shape. The ratio of volume stress to the volume strain within elastic limit is called bulk modulus. For this we have seen the example of a balloon. When we insert the air inside the balloon, we are inserting the air, that means we are changing the pressure, and because of that there is a change in shape body. The bulk modulus K equal to volume stress upon volume strain. So we can write volume stress as we have seen, it is dP, and volume strain, that is minus dV by V. So K equal to minus V dP upon dV, where negative sign indicates that the volume decreases if pressure increases and vice versa. The third modulus of elasticity, it is the modulus of rigidity. It is denoted by eta. The ratio of tangential stress to the shearing strain within elastic limits is called modulus of rigidity. The formula for modulus of rigidity, that is shearing stress upon shear strain. We have seen the example, that is of a rectangular box which is fixed at the lower end and tangential force is applied on the upper face. Then we have seen there is a change in shape. So the modulus of rigidity, the formula is shearing stress upon shear strain. Shear stress is F by A and shear strain we have seen theta. So the formula for modulus of rigidity, eta equal to F upon A theta. Only solid possesses this constant of elasticity. Thanks. If you have any queries, you can contact me on my email gr.bedare@gmail.com.